Okay, thanks for introducing me, and I'm glad to present our work of enhanced health recognition in the wild with data augmentation and the reduced modality of wearable sensors. So wearable sensors are well suitable for various health-related applications because they are unobtrusive, privacy-preserving, affordable, and user-friendly. But there are two challenges in front of us. The first challenge is how to train a robust model, especially when we have very limited labeled data. And the second question is, after we train a robust model, how can we deploy the model in the wild, especially with unexpected data corruption? So more specifically, the challenge one, because wearable sensors may have us to collect a large amount of time series data, but sometimes it can be very expensive to obtain the labels. So the question is, how can we train a robust model with a small number of limited data? And the challenge two is because different sensors, they can have complementary information. So multiple sensors are usually used in different applications. But for wearable-based application, especially for the application in the wild, we usually prefer less sensors because of different kind of reasons, like the device size, the cost, the energy consumption, constraint, and even the user preference. So the challenge is how to bring the model developed in the lab to applications in the wild with reduced sensors. So to solve the first challenge, actually there are different kind of approaches have been proposed. For us, we focus on maybe the simplest solution, data augmentation. And actually data augmentation is a standard component of the deep neural network training, but the application on health time series data is not well studied. So let's recap what is data augmentation. Data augmentation is a technique to increase the variation of the training data by applying random but realistic transformation to the existing training data. So the reason we need it because data augmentation can help us to generate more training data. Therefore, we can train a model that is more likely to generate well to the test data. And the data augmentation can be briefly defined as a transformation tau with a parameter alpha applied to the raw signal x. Then we can get the augmented data x hat. During our experiment, we explored the two different types of data augmentation. One is in the magnitude-based, including jittering, scaling, rotation, and magnitude warping. And the second is the time-based data augmentation, including permutation, time warping, and others. So here is the example of how the augmented data looks like after using different data augmentation. The first, each row represents the augmented data with different kind of data augmentation. And for each column represents the same data augmentation with different magnitude, which is the alpha in the previous equation. So we can see that not only the data augmentation method, but also the magnitude matters for the augmented signal. Through our experiment, we aim to answer the following questions. First is, for a given dataset, task, and a deep model, what is the most effective data augmentation method? And second, we want to know what are the factors that affect the selection of data augmentation. And the last but not the least is we want to explore the question, like why some data augmentation methods are more effective than others. And we evaluate different data augmentation on 7 datasets, including 2 ECG datasets, 2 EEG datasets, 1 ED, and 2 MU datasets, using 3 backbones, including the MLP, convolutional 1D, and also ResNet 1D. So here is the result of the 3 the result on the 7 data set with 3 backbones and 8 different kind of data augmentation. And we can find that the first, the bold number indicates the best performance, and the gray colored indicates the top 3 improvements in the individual row. And we can find that all the tasks can benefit from data augmentation, and the improvements actually can range from 0.5% all the way to 15%. And the next question is, what are the factors that, like the effectiveness of data augmentation? What are kind of factors that affect the selection of data augmentation? Let's take a look at this example with the PTP-XL dataset and the apnea dataset with the same backbone and the same data type. They both ECG signal, but they for different application. Like for the first one, PTP is for heart disease classification, and the second one is for sleep recognition. So as we can say, for PTP-XL dataset, the best data augmentation jittering scaling, while for apnea ECG, the best is rotation and permutation. So we may find that even the data type, the task, the backbone, those kind of factors may affect like how we choose the effective data augmentation. And also, for this one, we also notice that even though there's no such data augmentation methods that works equally well for different data sets, different tasks, but we find the permutation-based data augmentation, usually they have the most improvement than others, in more than like half of the whole experiment. So usually it's not a bad idea to try permutation-based data augmentation when you want to train a machine learning model on health time series data. And we also want to know like why some data augmentation methods are more effective by first summarizing the attributes of the desired data augmentation. So the first is challenge, which means the augmented data should be complex enough that a deep model must learn something to perform the task. But meanwhile, the data must not be that strong that makes the learning task impossible. So 2 desired attributes. The first is challenge, and the second is faithful. We also adapt the related work and use 2 metrics to quantitatively measure the 2 attributes. The challenge is defined as the ratio of the training loss with augmentation and also the training loss without augmentation. Meanwhile, the faithful is defined as the ratio of the accuracy on the validation data with augmentation and also the accuracy on validation data without augmentation. Here, the M is the model trained on the clean data without data augmentation, which means we use both the same model and valid on the validation data side. So here is the quantitative measurement. Let's first take a look at the figure C, which is an illustration of the concept. Here, there are 2 concept matters. The first one is the overlap. So the more overlap, the augmented data is more faithful. And the second factor is the size of the right circle. So the larger of the right circle, which means we can generate more challenging data set. And a desired augmented data should be in this quadrant, which means it's like a trade-off between faithful and also challenge. Okay, then we can take a look at the figure A and figure B. They are experiments on the PTP-XL and PMAP2 dataset. Each data point over here represents a model trained with a specific data augmentation. And as we can see, Okay, it's better visible. Okay, so on the top left, there are some red data points, which those data augmentation policy can generate a very challenging data set, but they are relatively very low in terms of phase fall. Therefore, this model actually negatively impacts the performance because the result is actually a negative 5 compared to the model trained without data augmentation. And a desired data augmentation is in this area. Oh, sorry. It's in this part. It's a trade-off between like generating more diverse data while remaining faithful. So to conclude, we conduct a comprehensive and systematic evaluation of A data augmentation on 7 hash time series data with 3 backbones. And we hope this work can shed some light on data augmentation for hash time series data, as usually a carefully selected data augmentation can outperform most of the claimed SODA method in the literature. And second, we summarize 2 desired attributes for an effective data augmentation and also adapt to metrics to quantitatively measure the 2 attributes. So we hope those can get us to further develop more effective data augmentation for hash time series data. And the next research will be something like currently, most of the data augmentation actually are either borrowed from or inspired by the work in other domain, especially for the research in computer vision. So how can we combine domain knowledge and develop some like physiologically inspired data augmentation, and also develop more efficient metric to measure the effectiveness of data augmentation? And also during our experiment, we also noticed that for some data augmentation, they can be very helpful for the recognition of class A, but meanwhile hurt the performance for recognizing class B. So exploring the class-dependent data augmentation will be another interesting topic in future. Okay, so let's talk about the second challenge, how to bring the model developed in the lab to application in the wild. And we propose a model-less framework. The framework can effectively fuse information from different modalities by encouraging positive knowledge transferring while avoiding negative knowledge transferring. And the framework can provide inference with reduced modalities when deployed in the wild. So let's look at 2 cases. The case 1, if modality M is more robust, contain more information, then the model, like the knowledge, will transfer from modality M to modality N. Therefore, we can also learn a good feature for modality N. The same case, if modality N is better than modality M, then the knowledge will transfer from N to M. Therefore, they can complement with each other and achieve better performance. We evaluated the framework on 2 datasets, including the SMEL dataset and also the test dataset. They're both in the wild dataset. So first, we want to demonstrate that whether different modality convey like the same information or not. To do that, we first train model based on the individual modality. For example, we use the GSR modality in the SMEL dataset and train the model. And here the gray color, which indicates the false prediction, and the yellow color indicates the true prediction. And also we use the ECG signal to train another model. And then we count for the consistent prediction. And we divide that number by the total tested samples. We can find that the ratio, actually, the consistency between the 2 modalities actually is less than 60%. So we made conclude that the different modalities contain complementary but different information, and we report the performance in the two datasets. And the first conclusion is naively fusing multiple modalities does not guarantee better performance. As we can see, the early fusion of the GSR and the ECG dataset model actually, the performance is not better than the GSR modality. And if we want to capture the complementary information, we need some carefully designed fusion mechanism. And also our proposed framework can not only improve the performance, like our performance is around 1 to 3% higher than the single modality and also the multiple modality, but also can provide inference with only a single modality. For example, our model is trained with two modalities, but we can provide inference with a single modality, like by only provide the GSR or only provide the ECG signal. A similar conclusion is also observed in the TAPS dataset. So to conclude, the reduced number of wearable sensors during deployment in the wild is more challenging, but desired for wearable sensor-based application. And the proposed M2L framework can not only leverage the complementary information of different modalities, but also able to make inference with reduced modalities during testing. And we hope this work can help to bridge the gap of model developed in the lab and also model deployment in the wild. Here is a reference, and I will take any question you may have.
Any questions from the floor?
Have you thought of a way of maybe quantitatively saying why is it the case that certain model works well with this type of data augmentation versus the other model is working well with another data augmentation? Let's say you have a new model that's not labeled and you don't have access to anything, and then you want to test it. If you could find a way, I was wondering if you could find a way to say why is it the case that it's working with this modality, and then that help you with new challenges that you don't know the label?
Yeah, that's a very good question. So you're asking about when you face a new data set, you don't have any label, you want to know what's the most effective data augmentation for that new data set. Yeah, so currently most of the data augmentation actually are, as I mentioned, either we borrow the idea or inspired by research in other domains. But it would be a very interesting future research to develop some physiologically inspired data augmentation. And there are, as far as I know, there are only a few of them in the literature. Yeah.
Thank you.
Let's take one more question. Over there.
Yeah, I have a question. So I'm curious why you choose transfer learning over something like co-learning or joint learning.
So you're asking about why I chose this?
Yeah, why you choose transfer learning to, I mean, I understand that your idea is you try to figure out which data source has better performance to enhance the other one, right?
Yeah.
But have you ever thought or tried and then decided to not using co-learning?
That's a good point. Maybe we can but actually the idea use the example over here. And we can see the different model, they can give the different prediction of the same testing samples, but they not always agree with each other. So that's why the constant prediction actually is kind of low. And we cannot say one model is always better than another. So the core idea is when modality A is better than, like, to predict the, those examples, then we choose to modality A. If like modality B is better to predict examples like the next maybe 10 examples, then we choose to modality B. So the core idea is to like which modality is more suitable for the prediction of the example, then we use that one.
Okay. Thank you.
So, no more.
Yeah, thank you very much, Dr. Yang.
Okay, thanks.